All right, continuing more with distributions. These are bar charts and histograms mostly is what we're talking about when we do this. So even more or something like that, more histogram stuff. Okay, so again, we want to look at this difference between a population and then various things dealing with samples and all that. So let's look at let's do the numbers. We'll go 1 through 6 like a die. Well, I don't know. Sure, we'll go, we'll keep it simple, 1 through 6. I could do 1 through 9 because we've got project things that do that, but 1 through 6 will take care of this just fine. Okay, so remember that if I roll a die a bunch of times, now what's a bunch? We'll just say a lot. For now, you know, what I expect from my population, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, is that I would expect my population comes up as each of these, according to my bar chart here, each of these is equally likely. And so if I say, okay, let's pick a number and let's make it a little easier on ourselves. Let's go with a multiple of 6 or something like that. So suppose I roll 30 times. Now, this is a sample. Okay, this is a sample because the population is really this theoretical thing of these outcomes for the die. I could get a 1, 2, 3, 4, 5, or 6, but when I actually roll it, I'm sampling from that population. And again, what could happen is I would expect usually to get something very similar looking. 1, 2, 3, 5, 6. Now, so 30 times. If I have 6 different numbers, 30 times 30 divided by 6 equals 5, you know, I would expect that I would get 5 each time, and you know, or 1/6 of the time, right? So that's the 30 divided by 6, or 30 times 1/6 is 5. Now, what might actually happen, right, is that the 1, I might get that. You know, maybe there's 6, 5, 4, 3, 2, and 1. You know, so we'll say that one had 6, and the 2 might have only had 4 in it. The 3 might have had the 5, which is exactly what we're expecting. The 4 might have only had 2, and the 5, well, what are we up to there? That's 17 out of 30, so we'll say the 5 had 7 of those and 6 6s, like that. So that might be one sample of rolling the die 30 times. We would have expected a bunch of 5s. This is what we got. Now, on the whole, this looks a lot like that. Now, this is where you have to get, you know, into a little more abstract ideas and notions about what looks like what. And, you know, but why do I think this bottom one looks a lot like the top one? Well, notice it's just as wide. I mean, all the numbers 1 through 6 are represented here. And as I look at the heights, you know, I wouldn't say that they're all the same height, but on the other hand, I wouldn't say there's like a definite peak anywhere or something like that, right? As I look at this, it goes down, goes back up, goes down, kind of goes up, goes in. So, you know, it's bouncing up and down. Well, that's because of the randomness of the sample. But, you know, there's no definite like peak on one end or the other, anything like that. And so if I were to do this a bunch of times, I would expect lots of things that look sort of like the top here, in that I would expect they'd be wide. Well, what do I mean by wide? Well, 1 through 6. And then, you know, that the heights would be more or less similar across, and I'd never really see, no matter how many of these I did, you know, I wouldn't come out of it probably thinking, oh yeah, I always get more 6s than 1s, or I always get more 3s and 4s than I get 1s and 6s, or something like that. Okay, so the sample, you know, I would expect a sample distribution. Okay, let's pull this down a little bit. I expect the sample distribution, okay, its bar chart or histogram. I expect the sample distribution to look a lot like the population distribution. Okay, that's a big deal. You know, I go take a sample, I look at it. If I took a good random sample, I would expect that my sample distribution, when I plot it, you know, when I look at a bar chart or a histogram of my sample data, that it would look a lot like the population itself. Okay, big idea there. Okay, that's what I expect. Now, what we want to look at is, suppose I did that same thing and I, instead of just looking at the dice, you know, I roll 30 times and take the average. Okay, so I roll 30 times, and I could do that with these data right up here. Right, I had 6 1s, 4 2s, 5 3s, 2 4s, 7 5s, and 6 6s. Well, let's think about what that is. Well, 6 1s, that makes 6. 4 2s, that makes 8. So I'm just adding all the numbers I got. 5 3s is 15. 2 4s is 8. 7 5s is 35, and 6 6s is 36. And that was a total of 30 numbers. So my X bar, or my sample average, is, well, let's see, 14, 29, 8 more is 37, with 35 is 72, and 36 is 108. So I think, if I added that right, 108 over 30. If I didn't, well, my grandfather always said, don't wreck a good story with facts. Okay, so my average here, 30 into 108, well, I don't have a calculator with me, but, you know, 3 goes into 10 3 times, so that'll be 3 point, and that's 18 left over, so I think that's 3.6. Okay, so my average that time, so I take the average, I'll get an answer, you know, this one, 3.6. Now, do it a lot. Again, what's a lot? I don't know, 20, 25 times or something like that. Now, when I do that, start thinking about it. Now, we'll see this. We'll actually, do some experiments with this, but just think about it. I mean, put some thought into what could happen, right? Now, what's the smallest I could ever get for my average? Well, I could roll all ones, okay? So my smallest X bar that I could possibly get would be 1, and my largest X bar that I could possibly get would be 6. That'd be all 6s. But when's the last time you saw somebody roll a die 30 times in a row randomly and get all 1s? Hardly going to happen, right? And and the same thing with all 6s. Now, if they did that, you would probably guess they were cheating. And so what's going to happen in this case is that 1, 2, 3, 4, 5, 6. Now, in this case, this really should be a histogram when I do this because, right, I could get an average of 3.6, I could get an average of 3.4, I could get all sorts of different averages. And so what we might see is, now if you look at, if I had all the same number, right, if these had all been all the same number, the same frequency, so if I'd gotten 5 of each of these, actually you can pretty quickly work out that the average of the numbers 1 to 6 there would be 3.5. And so what we're going to see is that now if I do a histogram, and I do this a lot, when I take the average, I really should see, now these are supposed to be coming down right in the middle. I'm going from 2.5 to 3.5 and 3.5 to 4.5 and so forth. But what we should see is, so these are pretty ugly histograms, but something kind of like this, okay, peaked in the middle in this case. And that looks very, very different from the population, right? So the population looked like that. A sample distribution looked kind of like the population, right? So that's what we said here. I expect the sample distribution to look a lot like the population distribution. However, if I take a sample and I do something like I take its average. Now, you have other items, we'll talk about those as well, standard deviation, medians, that kind of thing. Well, we could do the same thing with those. Instead of taking the average, we could take the standard deviation, we could take the median, we could find the interquartile range, we could find the range, which is the maximum minus the minimum. And we could do all those sorts of things for our sample. But if we do that, then this thing, this thing that we computed from our data is called a statistic. Okay, so that's in your text. So if we look at our distribution of a statistic, okay, and again, a statistic is just a computation from data. So it could be the average, it could be the minimum, it could be the maximum, it could be the standard deviation. Those are all statistics. So if I want to look at a distribution of a statistic, distribution is called a sampling distribution. Now notice how close that is to sample distribution. Sampling distribution is something like this, where I look at my frequency of my statistics, so in this case my average, my mean, sample mean. And when I do that, that's a sampling distribution. I do not expect I do not expect my sampling distributions terrible writing there, got cramped. I do not expect my sampling distributions to look like my population. Oops. Now, that's a general statement. Absolutely, I can make some sample, I can start with the right kind of distribution and then make a sampling distribution that looks a whole lot like the original distribution itself. But in general, I don't expect that. I don't expect that my sampling distribution looks like my population. Okay, so here was a case that, I think, without going into all the experiment and so forth, I think you can see that is that if I roll a die a bunch of times, my population, when I think of the population, I think of each of the numbers coming up equally, and so a given sample will kind of look like that. But if I'm looking at the average of those numbers, then I would expect that the average, that most of the time if I take, say, 30 rolls, when I do the average, most of the time it's going to be in here in the middle, and hardly ever will it be out here at these fringes. Okay, but again, just think about that. When have you seen somebody roll 30 ones in a row? Okay, so how am I going to get a low average if I can't roll lots of ones? How am I going to get a big average like 6 if I can't roll lots and lots of 6s? Because I probably won't. We just haven't seen that. Mostly I'll have numbers all over the place, but when I take that average, that will tend to be in toward the middle as the average, right? That's the whole idea. An average is a number of central tendency. And so a sampling distribution tends to look different than the population. And that, again, is a very important thing. Now, for us, we are going to look at, our sampling distributions of interest okay? We're only going to look at really one type of sampling distribution. Our sampling distributions of interest are sampling distributions, so I'll say that whole word again so we keep hearing it. Sampling distributions of X bar, okay, a sample mean. So in this class, that's our sampling distributions. We're going to care what the heck does the sampling distribution of X bar look like. And in general, that histogram is going to be, I can put it all kinds of places on the x-axis, but its general shape is going to be high in the middle and low out on the ends. Okay? A bell-shaped curve. So the sampling distribution of X bar is going to generally look like this. Again, if it's a small enough sample and so forth, it might start skewing things a little bit and, you know, kind of have that hump and be more toward the left or more toward the right with the hump. But pretty much it's going to have that hump sort of toward the middle, if not very much in the middle. Most of what we will work with, we want that hump very much in the middle. And so that, you know, this is the sampling distribution we're going to look at. Most is almost exclusively sampling distribution of X bar. Okay, again, different, very different in this case from the population distribution. Population distribution, very flat and wide down here. The sampling distribution, well, I could use that one. It's going to be peaked in the middle, our sampling distribution for X bar, peaked in the middle, very little on the ends, and actually the more rolls I make, what we'll see is the narrower and narrower and narrower that hump should be. So it'll get tighter and tighter, it'll get taller and taller in the middle, and almost nothing on the ends as I increase the number of rolls. Okay, so there is a bit on population versus sampling distributions. Very important idea for us.